All right, thank you everyone. So this week we'll be talking about loss functions. So in previous chapters we've talked about linear models and then shallow networks and then deep networks, and then now we're talking about loss functions. Um, so we'll start off just looking at some functions, so the log and the exponential. I won't spend very much time on this, but these are core to a lot of the different things that we'll be looking at today. So there's various different ways that you can formulate your machine learning problems. One of them is regression. So imagine you have some um, input. Um, and it can be all of these different variables, so square footage, bedrooms, etc. And then you have some output. Um, so like this is 340,000 for the amount, the home price. And then I will skip through some of the other examples so we can look at some of these graphs. So just imagine you're trying to predict height given some age, and you've got all of these data points, and you want to build some model in order to predict that pattern, essentially. Or you could do something like spam detection for email. So you have the number of words, and then you're trying to decide like, is this spam or not? And you can have a whole range of different possibilities there. And then another option with that is you could have length of tail, and that could be a variable that then helps you determine whether something's a dog, a snake, a lion, a lemur. So you can have several different classes like that. So one, you can draw a line through these points, but then you have to figure out how do I actually figure out the parameters to draw that line. And so one of the ways of looking at it is just drawing that line through, and then the other is looking at it from the probability perspective. So saying, given this age, what is the distribution of heights at this age? So if someone is, or if you look at 10-year-olds, not all 10-year-olds are the same height. There's all kinds of different variation of 10-year-olds, and it can be a different range. And there's some mean and there's some variance. And so you can view it as a probability at every different age. So at different ages, you have these different distributions. So you can see at all of these different points, you've got different distributions. And then looking at a classification problem, you kind of have the same thing because you actually have, at this point, there's a certain probability of it being a one and a certain probability of it being a zero. And so you can do the same thing here, saying at different numbers of words, you have a different probability of it being spam or not spam. And then you had the same thing with this multi-class example. So at this point, you have very high probability that it's going to be a dog, given that the length of the tail is some small value. And then if you look at the different lengths of tail, you can see that the probability distribution changes. So there's a certain probability of it being a dog, a snake, a lion, a lemur, etc. Um, and so here's kind of all of the examples shown side by side. So you can see at this given value, there's a certain probability distribution, and at this value, there's a different one. And this holds true for it can be regression or multi-class or binary. Um, so talking about the loss function is a measure of how wrong your model is, essentially. And the loss function that you choose is kind of telling you what your assumptions are about the distribution of the variable and the loss. Um, so you can change your entire model just based on which loss function and how you formulate things. So this is actually very important for your model. It's up there with architecture in terms of what your final outcome will end up being. So this always comes in the form of a single scalar. So you want to simplify things down to the point where it's like my loss is 0.3 or 0.4. You can have multiple losses, but once you go to actually optimize thing, you always want it to be a single number that you're just optimizing towards. So we typically minimize these values, so lower is better, and so that's the way that things are formulated. Um, so like looking at a 1D regression problem, you have some parameters. So this would be your bias, and this would be your slope. And then this is the line that comes given those parameters, and then you can measure your loss. So saying what is the error of all of these points summed together. And so this is where the critical bit comes in, is how you formulate this loss determines how you're going to correct this line, and then that will determine what your final optimal parameters end up being. So if you look at it this way, you can see, okay, it's always under predicting this value, so then I'm going to raise the bias or something like that. And so this ends up formulating our least squares loss function. So we have this is our bias term, and then this is our slope, and then this is our input x variable, and then you put these all together to say that's basically my prediction given the input here, and then you measure that against the actual value, and then you square that in order to always get positive value. So this is your squared loss function. And then you sum this across all the different points here. So that's how you get this 7.11 there. And so we'll talk about this more in later chapters, but you can optimize this with gradient descent, and so you can see it's slowly optimizing to lower loss, and then you're iterating and you're changing this line until you get something that fits it more closely. So now we'll be looking at how to construct loss functions. So the typical way that I have always thought of things is you have some x and you're predicting y given that. And so um, in the book, they actually kind of look at it slightly differently. And this was stretching me a little bit to understand how exactly the pieces fit together. So they were posing it as a conditional probability. So what's the probability of y given x? And then you have that full distribution of outcomes instead of just a single y every single time. Um, and your goal is to make it so that you are maximizing the probability given the actual value. Um, and so in a lot of our models, we will assume normal distribution, and so that's kind of just baked into the loss function. But if you pick a different loss function, you're kind of injecting a different assumption into what you're doing. And so with your model, what you'll actually be doing is be predicting this mean value here. And additionally, we'll look at it later, but you can also predict the variance as well. Um, so this is just looking at the reformulation, looking at it as a probability. Ted?
Yeah, I just wanted to, if you go back to the previous concept, you
Yep.
don't necessarily have to advance the slide, but like you were talking about, like whether you make a single prediction or whether you think of it as a distribution, this is like getting a little bit ahead of things. But if you make a single prediction, which is 100% this thing, zero everything else, it's actually not differentiable because basically you're going to get like infinity or zero as your various answers. So having something that's a full distribution where you're like, you can be very sure, you can be 99.9% sure, but at least if you have a full distribution, whether it be discrete or continuous, then at least uh, now it's differentiable for when we get to talking about how do we actually improve the weights.
Yeah. Any other questions, comments at this point? I haven't checked on chat. All right. Um, So one of the key problems with this is the product of this can be very, very small. So if you have low probabilities and you're multiplying all of these together, you can end up with just numerical problems where you've got values that are too small to even operate with. You'll get underflow. And so one of the tricks that people pull on this is they take the log of it and then they take the sum instead of taking the product. And so the reason that we can do this is that the log function is monotonic. So all of the peaks will be the same, all of the relative values will still be the same. And so it changes the magnitude and it allows you to take the sum instead of doing the product, and you don't lose a whole bunch of precision. And so people use this trick, and then because you're doing the sum instead of the product, you're not ending up with this numerical underflow problem. And so this is just a nice property in order to make it better for computers mostly. Um, so like we were mentioning before, you output this distribution, but ultimately in the end, you typically want a single value. So you can take the max of this distribution, and then you get your final point. Um, So this is what I was mentioning earlier. You can have a probability distribution, and a lot of the times we'll just assume normal, but in some of the example problems they talk about, you can do other things as well. So you want a distribution and a range that is relevant to your specific problem, and we'll talk about the different kind of formulations of that in a second. Um, so you want your model in order to predict the given mean or variance sometimes. Um, and then we will take some data and then we'll try to minimize against that. So like the example before, we have the univariate regression. So just this problem where you've got some input variables about a house, and then you want to predict its house price. So you're just a bunch of variables in and then single variable out, and then you have this sort of unbounded. It can be 0 to 100 million or whatever max house price. Um, and in reality, what you're doing is you're predicting this mean, and then depending on how you formulate it, you can just assume normal variance, or you can actually predict that out. Um, Gonna skip through. So this is actually a comparison that Ted made um, in a previous week, talking about the difference between the least squares and the maximum likelihood. So you can see one way of measuring this is just saying what is the difference on the y-axis from the true point, and then the maximum likelihood way is kind of saying with this probability distribution, what is the difference from the actual. And so you can see that this is looking at it like we were talking about before. So given an X, what is the distribution of possible outcomes? And so this one looks pretty good, but if we go to this one, we can see that the results are much worse. So this is one that isn't as well fit, and you can see like this is how it looks on least squares. But if you look at it from the maximum likelihood view, this is very, very heavily penalized because the parameters are currently saying the mean is here, and there's virtually no possibility for this outcome, but it is actually that outcome. So it's penalized extremely heavily because we're saying something is impossible, but it is actually within the realm of possibility. So it needs to adjust that parameter in order to get closer and put that in the realm of possibility. Um, Skipping through this. So one of the things about this is you can assume that the noise is always going to be normal. So looking back at here, we're just always assuming that the variance is going to be some fixed value. It's going to be up a bit and down a bit. But in reality, typically what you have with your data is something more like this, where you have greater uncertainty in certain regions of input. So if you have some data range, like you might have a house price that is, you have a whole bunch of houses that are between 500,000 and 1 million, but you have very few house prices that are in the $100 million range, for example. So you might have much greater variance on those. And so this is showing that concept of if you just assumed that there was always similar variance, you would end up kind of incorrectly incorrectly predicting the uncertainty. And so moving on to binary classification, this is a different formulation of this. So you have a single output again, but now you want it to be a probability rather than a regression. So a regression could be any number, but when you want it to be a probability for a given thing, you want it to be in the range between 0 and 1. So this is a slightly different formulation. Um, and so what you end up happening is the Bernoulli distribution, you have something where it's like this is the probability of it being 0, and then the probability of it being 1 is just 1 minus that. And so the way that we make that happen is we have to pass it through a sigmoid function. So your neural network or linear model or whatever will output some value that can be a massive range. So like imagine it could be -5 to 5, and then you take it and you pass it through the sigmoid, and then it will constrain it to be between 0 and 1. Um, and that will make it so whatever your positive is, it always your positive outcome and negative outcome always add up to 1, and so you have your true probability there. So this is the sigmoid function here, very very commonly used. Um, and so this is what it looks like when you pass some input through it. So you might have values of -1 to, or this is the input X, and this is the prediction out of it. And so you can have a value that's like 4, and then you pass it through a sigmoid, and because it was largely positive, it will end up a largely positive probability. And so the estimate here is this is your probability of 1 and this is your probability of 0, and in reality it's just 1 minus whatever your positive probability is. So binary cross entropy is a very, very important one. So I'll spend a little bit more time on this. So this equation, if we really split it into two parts, we have this bit over here, and then we have this bit over here. So I just want to kind of point out one characteristic here. Um, so if you, for example, had a label that was +1, you look at this, and then it becomes 1 minus 1, and then this whole bit just disappears, and then you only have this part over here. Um, and then the flip is also true. So if you had a label that was 0, then this whole bit is canceled out and you only have this bit over here. So that the equation is actually a bit more simple than it looks. You're only ever doing one of these unless you have some label value that is in between those. But in reality, a lot of the times it's just one side of this or the other. Um, and then what you're doing is you're taking your output and then you're passing it through a sigmoid, and then you're saying how far is it from the certain value, and then you're taking the log of it. So in reality, it's typically just the log of whatever your prediction is, and then the distance to the correct answer. Um, so binary cross entropy used in a lot of places, very important. Um, Here's this graph again, multi-class. So here's another formulation, a different problem that can be solved with these models. So you can have multi-class, so you can say, here's a picture of something, and then here's all of the different possible outcomes. You can have 1,000 different classes, for example, and you want to output a probability of it being any of these. Um, so the previous one, binary classification, was just a single thing, but you can have a multi-class, which is many different things. And the same as before, you want it to all add up to 1, so you have some probability and you have some understanding of the uncertainty there. Um, and so, for example, you have 5 different classes, and here's the probability of all of these, and they all have to add up to 1. And so this is the same as previous problems. Your neural network or linear model or whatever will output whatever it's going to output, and then you need to kind of constrain it or add an extra layer that will then make it um, always add up to one. And so the way that this is typically done is with the softmax function, and the softmax will it like its name suggests, it will be a softmax. So if you just took the maximum class and that was your prediction, then you would pass no signal to any of the other classes when you're doing learning. So you would upweight whatever your maximum was, but then you might not have any interaction with all of your other 1,000 classes. So you need softmax in order to pass the signal along to all of the classes at once. Um, so this is what it would look like when you pass something through the softmax function. So we have the probabilities of all of these different outcomes. So each of these lines is a different outcome. So you have the probability of class 3, probability of class 2, probability of or this is the raw output, so I shouldn't say probability, but this is the logit of F3, F2, F1, and then you pass it through the softmax, and what the softmax will do is it will up the weight of whatever the highest prediction was, and it will downscale the rest of them. But it will also make it so it's constrained so that these all add up to one. So if you add up this value and this value and this value, it will end up adding up to exactly one. And so you have your distribution of possibilities there. Um, so this is multi-class cross entropy. This is just basically doing similar thing, but with all of the different classes at once instead of just a single binary class. And this is a different formulation of it. Um, so this is just a bar view saying, look, the most likely outcome is class one, and then there's some probability of two and three. Um, so I'll skip through that part. They show some other data types. And then one of the things that they showed is that you can have multiple different outputs. So all of the stuff that we've shown so far has been like binary classification, but you can have multiple binary classification, or you can do regression, or you can do multiple regression outputs. And so the way you can formulate this is mostly the same, but you can say there's an extra summation here saying for all of your different um, classes or regressions or whatever you're doing. So can end up looking very similar. You just have an extra term there. Um, so this is showing you can have all these inputs, and then instead of just having a single input, you have or a single output, you have multiple outputs. So you can guess the freezing point and the boiling point at the same time. Um, So one of the problems from the problem set was actually asking if you're doing multiple regression and you're doing something like weight in kilos and height in meters, what's one of the problems with that? And one of the problems is that your uh, units are on different scales, and so that will also be factored into your loss. So if you have weight in kilos and it's 80 kilos, for example, and you have height in meters and it's only two or three, um, then your loss is going to be scaled accordingly. And so when you're actually optimizing, you'll probably put more weight towards optimizing the kilos than you will to the meters. And so one way around this is to scale your uh, outputs. So you would just renormalize it so it's between 0 and 1, for example, on both of them, and then you know that their magnitudes will be similar, their magnitudes and their variance. Um, so I think that's it for the slides. Any questions? Anyone want to look at anything in more detail?
So hey Ryan, so in practice, as far as going through these and having like the best educated guess to use first, what do you recommend for the torch loss functions?
I think it just depends on your problem. That's you are it depends on your assumptions about the problems, but it just varies if you're doing regression or classification or multi-class classification or something with images. There's all kinds of different uses that you could have for loss function. So I can't directly say which one is best.
Yeah, I'll add to that. Like what what hopefully the takeaway you got from this chapter, even if you didn't follow necessarily the equations, the technical details, is that you're trying to pick a natural, I'll call it a natural prior of how you think your data is distributed. Okay. And that's where the loss function comes in. So what you want is you want the loss function to penalize heavily something that is very unlikely given the data that you have as your training data. Okay. And so a housing price problem is very different from like an X-ray segmentation problem. And so you have to have a very different loss formulation because you have to have something that then just accurately captures what is and is not, um, considered reasonable, probable, likely, in the data that you have. I hope that makes sense.
Yeah, it makes sense, and I understand it's based on the problem there too. I mean, for optimizers, they typically say start with Atom, then go to SGD and that type of thing. I was wondering, if there's an equivalent for loss functions.
So there is, but only in the sense of if you've defined the problem. So for regression, the standard loss is squared loss, right? For binary classification, the standard loss is that binary cross entropy. For multi-class classification, it's using the softmax and doing full cross entropy and da 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 down the line. There is sort of like a standard, but if you just say like if you looked at the exercises at the end of the book, one of them is what if you're trying to pick a direction? And so like I'm going to use degrees. Every 360 degrees, your back pointed in the same direction. So you need some loss function that sort of understands that 359 and 1 are really close to each other, much more than like 1 and 10, even though they're, you know, in the literal sense, very far apart. They're 358 apart. So that's why you really need a loss function that understands your data.
Just want to add to this that we have a number of implemented loss functions, and it could be a good starting point for keras. For keras,
Yeah,
for
yeah.
TensorFlow.
But it might also be a little bit confusing if you're like, hey, look, here's 50, implemented loss functions. Like, it really is about the problem.
Yes, but I look up in the appendix here, and it looks like some functions are not even implemented. He points out two articles, which is not quite a good sign, especially when it is one article.
Yeah. So Ryan, you've got a whole PyTorch list on your screen.
Yeah. Yeah. And so even like in one of the problems, they're talking about uh where did it go?
I know there's the one on predicting direction.
Yeah, they had one that was about counts of pedestrians, and so they're talking about okay, build in this Poisson distribution, and you can do it by hand for the homework's sake, but there's also just Poisson NLL loss built into PyTorch. So if you wanted to,
Mhm.
you just take this and say, I have some assumption about my data. I think that it's about counts and it will be centered on this value. And then you can just take this loss out of the box and then go use that on your problem.
Yeah, that's very cool. Hey, Ryan, there's just one other thing in the chapter that I really liked. So I'm not going to ask you to find the slide because it's actually pretty early on in the slides. But at some point, it's like, hey, I've got 10 data points and I'm trying to figure out like what is the most likely, situation. And so you see that it has this formula. It has the pi notation where you just multiply the probabilities for each of those 10 data points. Okay, so this was super, super early on in your slides. And if you guys remember your probability, the probability of 10 things happening is only the product of their individual probabilities if those events are completely independent. Okay. And then if you assume something like they do for the simple example of regression, where the standard deviation is the same for all the different points, then what you're doing is you're assuming that these points are sort of identically distributed. They have equal variance, whatnot. And so you will hear people talk about us assuming that our data is IID. And that IID assumption actually directly is represented by which formula you choose here. Okay, so the fact that we take the simple route and we just multiply all the probabilities together, which once you take the log means you sum them together, that is because we are assuming independence. And you can very easily break an algorithm, a model, if you give it data that's not IID. So if you're predicting the height of a kid based on age and gender, and for whatever reason, all the boys were malnourished and all the girls were well fed, that is going to completely break your model. Okay, you're going to have a very inaccurate prediction because it is no longer IID. There is this heavy correlation amongst the boys. There is this heavy correlation amongst the girls. So I thought that was really cool because I've known about it and it was kind of intuitive, but it never really sunk in for me, Ryan, that like the equation for calculating loss fundamentally depends on that assumption.
Yeah. I think that's all I've got, unless any questions?
So maybe we want to see if people have any questions, if anybody has looked at the problems, tried the problems. And then I had just an oversimplistic example I was going to share, but I don't have a slide or anything. I'm going to have to just sort of like freehand draw it and share it with you guys. So let me just start first and see if anybody already has a question about any of the problems. Yeah. Got a
Yes,
hand
so
raised.
in that example, where all the boys are malnourished and girls are well fed, how exactly will the model break and how would you fix it?
There is, I mean, in the extreme where it's that way, okay, I'm assuming that you don't actually know there's this hidden correlation, okay? You just have this data and there's this terrible correlation. Then what's going to happen is, let's say on average, you're malnourished, you're going to be shorter, right? Your model is going to underpredict the height of boys, and the girls are either relatively overpredicted or accurate or whatever, right? So if you try to use this model on a population where nobody's malnourished, nobody's underfed, it's just going to do really badly. And there is no way to fix it because you have no accurate data on boys. So that's a very extreme example. Gosh, I don't know if I can think on the fly of another example. Ryan, I don't know if you can think of one where like you can sort of like eliminate certain data points so that you're not over-representing certain correlations or whatever.
I don't have an example of that, but I was just gonna say
Okay.
I've been working with some image stuff where I'm trying to segment some things, And I can end up with this bizarre scenario where it just always guesses that the center pixel is going to be lit up because of the way that I've sampled the points. And so that's another one of those tricky things with you assume that it's IID and that it's randomly sampled, but if you pull your data in the wrong way, you can bake something into your model that isn't true. And so I wouldn't say that it's necessarily collapse of your model, but you've taught your model something that isn't the reality of the data because of how you've sampled or something related to that.
Yeah. Oh, that's great. Yeah. So there's this one example that I love to share with people. I apologize if some of you have heard me talk about this before, but there was a study that these people did. They took like 3 hospital systems and they had x-rays of whatever. So I'm just going to just say it's lung cancer, okay, for simplicity. And they wanted to build a cancer prediction model. And so they built the model, and on the training and the validation sets, it looked pretty good. And so then they got some more data, and basically what they found was that the prevalence of lung cancer at the 3 different geographies where those hospitals were located was fundamentally different. Okay, so let's just say like one of the locations, the prevalence was twice as high. And so basically, even with clean images, the model would just predict lung cancer twice as much for that one city. So like, what's going on? And they realized like, oh, well, they use different X-ray machines. And so like in that one city, the X-ray comes out like 4,000 by 3,000 pixels. And then in the other city, it's 3,600 by 3,200, whatever. And so it's like really obvious that like this picture came from that one city. So then they resized all the images and retrained the model. And the exact same thing still happened. And I don't know exactly what they did, if they did some like what's the activation mapping thing for images? I forget what it's called. But they figured out like, oh, on each X-ray, there's a little metal object that's like the name tag. It has like your patient info, hospital info, or whatever. And like in one city, they're like oval shaped, and the other ones they're rectangles. And so then they like cropped that out. And then the model kept doing the same thing. And so like they ultimately failed. They could not find a way to make all the images uniform enough that the model couldn't cheat and figure out which hospital it came from. So I'm sure they kept working on it, but at the time of the article that I read, they had utterly failed. They could not find a way to remove that bias. The model was just like, oh, Chicago, I'm going to predict a lot more than, Cleveland. It was crazy. But there's that bias. They just had a lot more lung cancer there. So
That is very interesting. Thank you. This is a little bit like the model training against the snow in the background, right? When it predicts dog versus wolves.
Yep, we had that like US versus Soviet tanks, same thing, looking for snow. So in those cases, it's pretty clear what the spurious correlations are. So if you remove those, right, you're good. But sometimes you have other correlations that you don't know about, and you always have to be careful. Thanks for the question. Yeah. Next, John, go ahead. I see you're unmuted in Zoom, John, but we don't hear you. I don't know if there's a problem with your microphone.
Can you hear me now?
Ah,
Sorry about that. So on the issue of malnutrition, could you make it a dummy variable where you have like malnutrition would be 1 and 0 would be well fed, and or would that still matter?
yeah. If you ultimately figured out that was the problem with your data, you could certainly add another variable, a dummy variable for that. And then if it wasn't 100% of the boys, if you had a mix, then you would at least have some boys who were not malnourished, and you could get accurate predictions for like what well-fed boys look like, right? But in most real world cases, you don't necessarily know what that hidden correlation is. And worse yet, once you find out about it, you don't have accurate labels to tell you exactly which boys are malnourished or not. So it's really like, so what you're saying is exactly right. And if you're lucky enough that you can label it or get whatever, but in some cases, what you have to do is you just have to make sure. So here's like a simpler example. You're building an X-ray model, and you've got a whole bunch of X-rays from hospital X. What'll happen in that data set is you'll get multiple X-rays of the same patient. And if you have some of those same patients in the validation set, even though they're technically different images, but because they're the same patient that was in the training set, your validation scores will be higher than what you will see in the real world. Not horribly higher, but higher. So a simple thing then you could do would be to say, I will limit it to one training image per patient. There's other things you could do. You could stratify, whatever. But like that would be an example of eliminating those correlations between examples in your data by saying I'll have max one chest X-ray per person.
Thank you.
Cool. Thanks for the question. Anybody else? All right. I think there's a few problems we can just kind of high level talk through. But I was just gonna share with you guys like a sort of a simplistic scenario here. So make that a little bigger. All right, so I apologize for the low tech tools here. But let's say you had like 5 data points and you've got 4 of them that are just like pretty, right on a nice line. Okay. And then one of them that's like way different from that. Okay. So if you assume that these are distributed Gaussian, like normally or whatever, okay, then what does this line look like? I'm not going to be able to draw it like super well, but like the line that goes through these 4 points is going to look something like this. Okay, so your prediction for this X value is going to be oops, switch back. It's going to be like way up here. And so the difference in your predictions is this height over here. Okay. Now, if you guys are familiar with like a Gaussian distribution, it's a bell curve. And so as you get towards the tails, this becomes very, very unlikely. So you see, at 3 standard deviations, right, the probability is what, like around 0.5%, or I don't know, something around there, right? 4 standard deviations out, it gets even smaller. So you're talking about like pretty small numbers. So normal distribution gives us this squared error. What if you didn't square it, what if you just took the absolute value? What if you did mean absolute error? I think that was on like that table in the book, Ryan. Okay. But what that means is then you're not penalizing this thing from being for being so far by nearly as much. The squared penalty grows quite a bit. And so this would represent a much flatter distribution, a much more heavy-tailed distribution with a lower peak in the middle. And so this would represent data where you think that this is, much more reasonable. So if you were measuring the size of mice or something like that, you might expect that, there is a very narrow range for the size of your mice based on, I don't even know how much they ate or availability of food or something like that or whatever. But maybe there's other animals. I don't know. I'm going to guess goldfish, but I don't know if that's true. Where like the size of the goldfish based on availability of food can have like much broader range. And so this could actually like, be a valid point or whatever, right? So what would happen if you use the squared error is that the actual line you get will look something like this. Oh, I'm not using the line tool. It'll look something like this because it wants to be relatively close to every point because there's a huge penalty. But if you use mean absolute error, then maybe you, oh, geez. Okay, be that way. Then maybe you get a line that looks more like this. Okay, where it gets pulled down. So again, this is where you need to say, as the scientist, what do I think the distribution of my data looks like? How realistic is this? And then I will decide how much I will penalize. You know, the reality is like any loss function that if your difference is bigger gives you a bigger number will kind of work. But it'll give you a different answer. So this is a very simplistic answer with just like, you know, one input, one output, and 5 data points. But you can see that ultimately what they're trying to do, you know, how they're trying to conform. And so normally if you use something like a Gaussian type distribution, what it's telling you is that I believe my training data is real. I don't think that anything in there is far off from what you should expect for future examples. I'm going to penalize very heavily if you have a large error. Then what that means is that your model is going to really, really, really work hard to hit all the points. So question in the chat, could you remove this point as an outlier? Yes. So if you think this is actual measurement error, so if you're measuring the temperature of an office building and you have, you know, 68 degrees, 71 degrees, 69 degrees, 72 degrees, 0 degrees. Well, was the office building actually 0 degrees, or do we think that this is actually an error? So if you think it's an error, then it makes sense to declare it an outlier and delete it. But you really have to decide for your data, is this a goldfish that really was a lot smaller than we thought it would be just because of whatever other conditions other than my X, which is like availability of food. So I picked this because I thought I heard somewhere that like goldfish can grow like based on the size of their container. So like a goldfish in a bowl, I guess they might overeat, but like with abundant food will only get to be, you know, 2 inches long. A goldfish in a big 5-foot tank might get to be 8 inches long. And then I saw a photo of some guy that actually caught a goldfish in a lake, and it was like as big as him. You know, it was like 200 pounds, and it was like 3 feet long or something like that. Can you use Grubb's t-test on data? So I'm not super familiar with Grubb's, but any kind of statistical test you do, you must formally declare what your hypothesis is. You have to be very careful about this. So if you don't know how the data is distributed, then you can't really formulate a strong hypothesis. So if I formulate a hypothesis, blah, 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 then there will be a test I can do to see if my data looks like it fits. So if I say blah, blah, blah is the distribution, then I can test it. But there is no just sort of like magic test. There's no magic test that tells you this is an outlier. There's always some prior that you're basing, you know, your thinking on. And then what frequentist statistics will tell you with something like a t-test is, given what your assumptions are that you put in as your prior, how unlikely is it that you're going to see something like this? And it's still never a true false, but you can decide that, hey, if it's less than 1 in 1,000, then I'm just going to treat this as an outlier. But again, it's still not like an oracle. It's not super ground truth.
I just want to add to the previous discussion about absolute value and square.
Mhm.
The thing is that absolute value function has the break over derivative at one point. And when it is a few such breaks, it is fine. But when you have a whole sum of such values, you have a lot of breaks like this. It takes much longer to compute. It is computationally more expensive. And once in a while, I hope that they deal with it and come up with some way to optimize it. Just, a small hope. And I run a neural network with such, with mean value error, but they still didn't.
People use Huber loss, Maya, in order to sort of avoid the ugliness of absolute value.
Yes, Huber loss is not differentiable at each point. It is the same. Well, it is some improvement, but because it is differentiated in the middle, but it still have breaks. So you can try it. I think I've tried. I don't remember with what, but it is longer too.
Yeah, we can get like super technical. I think people use subgradients, and that works perfectly fine for most SGD like optimizers.
I tried in practice. Okay.
Okay. I have not done a lot, so I trust you on that. All right. So I hope in terms of intuition, this is again a very simplistic 1D example, but it gives you the message the author is trying to tell you is that if you know how you think your data is distributed, then you can create a loss function that penalizes things that are unlikely and welcomes things that are very reasonable with your data. And you need to have a function that has the proper bounds. So if your data can only be a probability between 0 and 1, you don't want your model to output a prediction of 2. It's nonsensical. We don't know what to do with that, right? So that's why we use something like the sigmoid function. All right. There are other functions you can use. You can use probit. You could use all sorts of functions. Any function that will bound things between 0 and 1 will technically work. It's just that they will have different amounts of penalty on how far you are from the right prediction. And so it's really up to you ultimately to decide how much do I want to penalize things. And that will give you slightly different answers. This is, of course, a very extreme example because I picked a point that was very far away and I only have 5 points, right? It's not going to make as much of a difference if you're doing image segmentation. In fact, Ryan, I would say that like when we've played with changing the loss, it's like I actually am hoping it'll do something different, and it looks like I got pretty much the exact same predictions. Yeah. So I hope that helps just in terms of like the overall message.
Just thinking about this because you mentioned only having 5 points. If you look at that and you just add additional points on your line, like if instead of having 4 on the left side, you had 50, the weighting would I'm just thinking about how that would scale. You would still be pulled very, very heavily by the 1 point.
Right. The green line, where's my mouse? The green line, the more points you have over here, instead of 4, you have 50, then the green line's going to be a lot closer to the red line because you're going to get 49 votes for near the red line and only 1 vote for near this point. But it will still. And then there's particular phenomenon of regression. If this point was very far, but it was in the middle, it would have actually a lot less effect than if it's far to the right or far to the left. So there's this leverage effect that happens with regression. And that's one of the things that people dislike about regression is that outliers, again, this is a single valued input. Outliers that are far to the left and right have more leverage than ones in the middle. And so it's not a very uniform behavior of how outliers work. And that makes it harder to theoretically understand I think, for example, Ryan, a tree-based model would still be affected by the outlier, but it would be sort of more uniformly affected whether the outlier was in the middle or on the ends. And you still might not like the prediction because maybe on a tree, it would just take the red line, it would lower the whole thing. Like the slope would be similar to the whole thing, right? So not saying there's a free lunch, just that like if you understand your assumptions, then you can understand what your loss function and what we're talking about deep learning in this book, in the UDL book, but even for other models, there's sort of an analogous conversation we can have about
Yeah.
what your assumptions are and what it does. Yes, so I was saying, by the way, it's not like I calculated, but I was saying that the squared loss would have a green line that's pretty close to this point because this is the squared loss really, really, really penalizes when you're far compared to something that was more like absolute error, then be like, oh, okay, well, you know. So like just imagine that like, you know, this thing is off by 100 and these things are off by 1, right? You square 1 and you're still at 1, you're off by 100 uses 10,000. So it doesn't matter if you have 50 points, doesn't matter if you have 1,000 points over here. This one thing with a squared loss of 10,000 is going to yank your line. Again, it takes a very extreme outlier and it takes the outlier being way on the right, but that can happen to your regression model.
Okay, I looked up Huber loss. Sorry, it is my mistake. There is no break of variable, but we still change the formula, so it can slow down the computations.
Yep. Yeah. So if you do want something with a smaller penalty than squared, you can use Huber. All right, I think we'll wrap up here. We're a little past the top of the hour. We do have office hours that we normally start at 1, but that doesn't mean you can't ask any more questions. We can just open the floor so that we'll have a mix of either questions about deep learning or any other topics. I didn't actually hear any dings, so I don't know if we have new people who arrived, but we'll just, I think, stop the recording here and shift gears.